All right, welcome, ladies and gentlemen, to 8.5. You might understand this that we did not do 8.4, and it's not actually necessary for us. All right, so what we're going to look at is some polar equations of conic sections. So we just got done with dealing with all of our conic sections, and now what we need to do is we need to look at how can we transform this into polar mode. Why, you might ask? Well, that's basically one of the things that we deal with pre-calculus is the study of polar graphs, polar equations, polar mode, and things like that. So we're actually going to be able to figure out how to graph conic sections on our calculator using polar mode. So we can actually graph these non-functions. We can graph ellipses and hyperbolas and parabolas, sideways parabolas. All right, so couple little things we got to remember is these three basic things, stuff we actually learned about in our first three sections. It has to do with eccentricity. If eccentricity is bigger than 1, it's a hyperbola. If eccentricity is equal to 1, it's a parabola. And if eccentricity is between 0 and 1, then it's automatically an ellipse. And the reason we need to know that is because the polar equations actually deal with eccentricity. And eccentricity is actually a part of the equations. Now, we're not going to go through how we get some of these formulas, actually any of these formulas. What we are going to look at is what is happening. What I actually want to do is I want to think about first, what was polar mode? Some of you are going like, I don't remember what polar mode was. And what polar mode was when we were looking at things like coordinates on a graph that were r comma theta, where we had what was called the pole, and we had a positive axis. And that's actually the only axis that we had, technically. And what r comma theta was we went to some angle theta, and r comma theta was just some distance r from the pole. So that meant if I was to do the 3 comma pi fourths, this could actually be pretty close to this, where r is equal to 3 and theta is equal to pi fourths. That's actually pretty close to a representation here. That's what polar mode was. The other thing of polar mode that you got to remember is this could actually also be written as a negative r value. If I said this is negative 3, and I went to, what is that, 1, 2, 3, 4, 5 pi over 4. I would have to go all the way out here to 5 pi over 4. But instead of going in the positive direction, I would have to go in the negative direction back here. So we could rewrite this as two different things. So there are reasons we need to know these negative coordinates in polar mode. Just little things you need to know. Sorry about that door there. All right, so let's look at the standard form. We have 4 different standard forms. And the reason these are necessary is because every single polar equation that we're going to be dealing with in this section has this one statement right here. Very important. For a parabola, its only focus is at the origin or at the pole. For all of the other ones, at least one, not at least, there is one of the foci at the pole or at the origin, which means if I was to give you a graph like this and there's your pole, all of our graphs are going to go around in every way. And you notice that there's actually 4 different ways. We can go to the right, we can go up, left, and down. So we get 4 different equations. So what we're going to do is we're just going to sketch a little graph for each of these. So for the 1 plus, notice what's different really in all 4 of these. 1 plus e cosine, 1 minus e cosine, 1 plus e cosine, 1 plus e sine, 1 minus e sine. And k is the directrix, and e, which I didn't write up here, is, you might have guessed it, eccentricity. So for this version, the first one here, this is for the pole is one of my focus points. This is the direction that this particular conic section moves. It could be a parabola, it could be a hyperbola, where the other side's out here. It could be an ellipse where it goes this direction, short and fat. And out here is x equals k, the directrix. And you might guess that since the plus cosine is this way, the minus cosine is the other direction. And you'd be right. And again, this is x equals negative k, the opposite of k. And you could probably even guess that since this is left and right, the other two ones, the sign, are up and down, and you're right. You might be confused at which one they are, though. For the positive sign, this is the ellipse, not ellipse, but the conic section going this direction. And we have the directrix y equals k. And the last one is the up version, if you want to call it the up version, where we have the directrix y equals the opposite of k. All right, so what you need to know is how each of these equations are going to be oriented, what the equation's going to be, or what is it going to be. I mean, it just comes down to what is E. So we need to know what's the eccentricity in order to figure out what type of conic section it is. And then eventually we're going to be converting between polar mode and rectangular mode. So let's start off with the first three questions here. With the focus at the pole, write a polar equation for the specific conic section. So if eccentricity is 3/5 and the directrix is x equals 2, well, we would look at that and we'd go, oh, if the directrix is x equals, that's going to be either of the first two equations. And because x is a positive number here, that means it's going to open to the left. So basically saying we're going to get orientation like this, because x equals 2 is out here. And then it just comes down to plugging it into your equation. You're given, I'm going to write it up here so I can delete them, r equals ke over 1 plus e cosine theta. And you just plug in what you know. You know k is 2. E is 3/5. I don't know why I didn't write a 2 right there. Over 1 plus 3/5 cosine theta. And like you know, I don't like fractions in our inside fractions or decimals inside fractions. So I can multiply top and bottom by 5 in order to cancel these 5s out of here. Well, 2 times 3 times 5 divided by 5, that's 5s are going to cancel. So 2 times 3 is 6 over 5 times 1, which is 5. 5 times 3/5 is 3, and cosine theta. And there we go. We can actually, that's it. That's our entire equation for the polar mode. So some of these problems are going to be kind of easy, others not so much. Let's try the next one here. Eccentricity is 1. Well, if eccentricity is 1, that means it's a parabola. By the way, this first one meant that it was an ellipse, and the last one here is a hyperbola. Directrix is x equals negative 2. So that means we have x equals negative 2 as a directrix, which means it's going to open to the right. And we have r equals k. Well, in this case, k is not -2. K is actually just 2, because this just tells me the opposite of k. So k is actually 2, so be careful with that one. K is 2, e is 1, and I get 1 plus, oops, sorry, not plus, because it is opening to the right, so it's actually 1 minus, I gotta scratch because I have no eraser on this, 1 minus e, which is 1 cosine theta, and we just simplify, get rid of the parentheses. We're going to say it's 2 over 1 minus cosine theta, and there we go. We have a parabola opening to the right in polar mode. All right, last one here. This is a hyperbola. And the hyperbola has a directrix of y equals 4, which is up here, which means it opens down like this and up like this. And because the focus is here, this is one that opens down. So this is a KE, so we've got r equals KE over 1 plus e sine of x. So, or theta, I guess, whichever one you want to deal with there. Equals, all right, so k in this case is 4. E is 3/2 over 1 plus 3/2 sine of theta. Multiply top and bottom by 2 to cancel out those 2's, and I get a 12 over 2 plus 3 sine theta. And that's actually it. These types of problems are not meant to be challenging. Maybe the next ones, I don't know. The next ones, again, are not too hard. You just got to pay attention to what the equation is saying. So you need to determine the eccentricity and the type of conic and the directrix. So kind of going backwards like up here. So in order to determine the eccentricity, you actually need, if you've been kind of looking at this, that 2 can't be a 2. That 2 has to be a 1. So I'm going to divide top and bottom by 2. So I'm going to get a 3 over 1 plus 3/2 cosine theta. So eccentricity in this case is 3/2, which is bigger than 1, and therefore it's a hyperbola. And then the other part to this is, where's the directrix? We know that k times e is equal to 3, and we know that e is 3/2. So we know that 3/2 k is equal to 3. So multiply by 2, divide by 3, I get that k is equal to 2. And then we just have to figure out, is it x equals 2, x equals -2? It all comes down to the fact that this is a plus cosine, which means that my directrix is x equals whatever k is. So it's 2 in this case. And there we go. And the second one is exactly the same way. So this I'm going to divide by 4. So 6 over 4 is actually 3 over 2. 1 minus 3/4 sine theta. So E is equal to 3/4, which is less than 1, which means it's an ellipse. I then need to look at the fact that 3/2 is equal to k times e, which is 3/4, multiply by the reciprocal. I'm going to get k equals 2. I get k equals 2 again. And which way is it going? So this is a minus sign. So this is an open up. So my directrix is y equals the opposite of k. All right, so those are our easy problems, quote unquote easy problems. So let's move on to something a little bit more challenging. And I'm actually going to start from the bottom up on this one. And I may or may not do all 4 of these. At least start with a couple of them. Now this might be different from how textbooks solve these problems or how Slater solves these problems or anybody else, but I solve them this direction. I use everything that I know from the first 3 sections and a little bit of what I know for polar equations. So let's take this one right here. Let's take this one on the top right. This is a plus cosine version. So I know, first of all, that it goes like this because it's plus cosine. I then also know that E is equal to 1, and when E is equal to 1, it's a parabola. So that's good. That tells me I have a parabola right here. So it would probably be good to know what is the vertex. Because the vertex is going to tell me everything I need to know about a parabola. The vertex, notice where the vertex lies. This lies when theta is equal to 0. And when theta equals 0, I can just plug that in. I know that r is equal to 4 over 1 plus cosine of 0. Cosine of 0 is 1. 1 plus 1 is 2. And 4 over 2 is 2. That means in rectangular, or by the way, this is Cartesian, same thing as rectangular. That means if I was to graph this, it would be at 2. And my vertex would be at 2. Well, I automatically know that the pole is one of the focal points, or is the focal point. That means that P is equal to 2. And that's actually everything I need to know to go into rectangular mode. This just tells me it's, because it opens to the left, it's a y squared, and y is not moving at all, so it's y squared equals 4 times P, which is 8, times x minus 2, because my vertex is at 2, 0. All right, so notice what I did. I just figured out where is my vertex, and then I used that to figure out where everything else was at. And now I have the rectangular mode of a polar equation. Let's try again here. Let's try this one with the 35 here. Well, first of all, this is a minus sign. So minus sign, if I was to just do a sketch, tells me it does this. If I divided by 2, this would be 35 over 2, this would be a 1, and this would be a 7 over 2. And 7 over 2 tells me hyperbola, so it's going to go like this. Now, the reason I'm doing this one is because hyperbolas mess people up. Because they want to plug in order to find the 2 vertices, they want to try to plug in 3 pi halves for both of them. But can't do that. What we are going to do is we're just going to plug in 3 pi halves first. So up here is pi halves, and down here is 3 pi halves. And if I plug in pi halves, I get 35 over 2 minus 7. Well, sine of pi halves is 1. And 2 minus 7 is negative 5. And 35 divided by negative 5 is negative 7. And then I'm going to plug in 3 pi halves. And 3 pi halves, sine of 3 pi halves is -1. So this becomes a +7. And 35 over 9. Well, that's really ugly. But guess what? We're okay with ugly numbers. We better be anyway. Okay, now what? What do those even tell me? Well, 35 over 9, if you were to calculate this out a little bit, 35 divided by 9 is, 35 divided by 9 is actually 3.8 repeated. And that means when I go to graph this, this point is, what is that? That's actually 3 and 8/9. And this point is down here at 7, or 7 units from the origin because it's in the negative direction from pi halves. Now, what does that mean for us? Well, that means we have to do some ugly math, I guess. I need to figure out, you got to remember that our equations are, in this case, y, whoa, what happened there? A y minus k squared over a squared minus x minus h squared over b squared equals 1. So I got to figure out h and k. Well, h and k, I know what h is. H is 0 because it doesn't move left or right. That's good. That's all I got so far. And then for k, k is halfway between those two vertices. Oh, that means we got some ugly stuff to be doing here, huh? Well, in this case, 7, in case you were wondering, is the same thing as 63 over 9. And I want to find what's halfway between 63/9 and 35/9. How am I going to do that? Well, probably just find how far away are these. These are a total of, what is that, 28 units apart. Half of that is 14, so right in the middle is going to be 14 units from either of these, which is going to be 49 over 9. Well, that's our ugly k value. So it's y minus 49 over 9 squared. Now I got to figure out A, B, and C. Well, oh man, these are getting ugly. A is the distance from center to vertex. Well, I just figured that out. A is the center to vertex. Oops, sorry, not 28, but half of that, 14. 14 over 9. So that's A. So that's A. That's the distance from that center point to either of these points. And A squared is going to be 196 over 81. Wish this pen worked a little bit better. So A squared is 196 over 81. And you got to remember that when you put that into fraction, the 81 goes on top, and the 196 goes in the bottom. Now I got to figure out B squared. Well, B squared is going to be that kind of ugly stuff to find. And B squared is found using A squared and C squared. Oh, man, it looks like math going to be ugly. So we know that C squared is equal to A squared plus B squared. C squared is the distance from center to focus. Well, that's 49 over 9. That's C, actually. So C squared is a really ugly 2401 over 81. A squared was 196 over 81. So I could subtract and find b squared. So 2401 minus 196 is 2205. So I get an 81 in the numerator and 2205 in the denominator. This, I forgot, was probably one of the ugliest problems that we do in this entire lesson. And of course, it just got erased. So, lovely PowerPoint working out for me here. So we should have gotten an 81 times y minus 49 over 9 squared all over, what was that? That was 196 minus 81 times x, man, things mess up on me, I get all flustered. X squared over 2205 equals 1. Yes, it's ugly. Is it still math? Is it still relevant? Of course. But here's what I want you to pay attention to. Whenever I am looking at these equations, first thing I do is I go, what's the orientation? Okay, if I think about this one. Minus cosine says it has to be oriented like this, whatever type of function it is. 3 over 5 is going to be eccentricity, which means it's less than 1, which means it's an ellipse. And then all I have to do is I have to figure out what are these vertices. And in this particular case, this is for theta equals 0, and this over here is for theta equals pi. So I plug those in, and I figure out what are the coordinates in rectangular mode of those 2 points. And then I can do exactly what we did in 8.1 through 8.3. Figure out where's the center. I know my focal point is at 0, 0, which makes a little bit of your math easier. And then I do exactly what we did in 8.1, 8.2, and 8.3. Okay, so I'm going to hold off on those ones. If you have questions on them, you come see me. We'll be working on this for a couple of days, so make sure we got this down. Now this brings us to these two examples here. So you need to look at them and go, okay, what does this mean? We have a hyperbola, and it has transverse axis endpoints of 3, 0 and negative 15, 0. 3, 0 and negative 15 pi. Now this is 3, 0 because we go 0 radians. You got to remember that these are in polar mode. We go 3 units away in the 0 theta. But here, if we go to pi radians out here, but we go in the negative 15 direction, we have this point here. This is 15. This is 3. And we want the polar equation. Now, because these are vertices, this opens like this and like this. Now, the reason we need to know that is because the opening to the left means it's r equals ke over 1 plus e cosine theta. Now, in order to write the equation, we need to know what is k and what is e. And it's actually not that hard to figure out. We know that if we plug in 0 for theta, we should get r equals 3. So I'm going to use that to our advantage. I'm going to say that 3 is equal to ke over 1 plus e times cosine of 0. Cosine of 0 is just 1. And I'm going to get rid of this fraction. I'm going to cross multiply technically. 3 plus 3e equals ke. Then I'm given a second point. So let's use that second point. I know that r is negative 15 when I plug in pi. Cosine of pi is negative 1. And if I cross multiply this gets a negative 15. And this is a minus 15 and a minus e, so it's actually plus 15e equals ke. Well, you'll look at here and you go, hey, look at that. I have 2 ke's. That means these two things are equal. Simple substitution right there. And if I add 15 to both sides and subtract 3e, I get 18 equals 12e. And you can get e is equal to 3 over 2. And once you get e is 3 over 2, you can solve for k and just plug things back into your equation. And when you solve for k, you get that k is equal to 5. You plug in k, you plug in e, and you get your equation r equals, where do I have room here? R equals k times e. So 5 times 3 halves is 15 halves over 1 plus e, which is 3 halves, cosine theta. But we don't like those halves there, so technically this 2 is dropping down, or you multiply top and bottom by 2, and you get this really lovely equation of 15 over 2 plus 3 cosine theta. And you can actually graph this on your calculator now. And you'll get a hyperbola graphed very nicely on your calculator with these two vertices. All right, so notice what I did. All I did was I figured out where do these points go, what's my orientation, what type of equation am I going to use. I'm going to plug in my 2 thetas, solve for e, solve for k, plug it in, and there's your equation. All right, so this is going to take practice. Hope you guys got a lot out of this, and work hard. I'll see you guys tomorrow.